for this video, we're going to be looking at what is a matrix and how can I operate with matrices, and then what are some of the properties that I'm limited to with these operations. So a matrix is a rectangular array of numbers or expressions. So an example of a matrix would be this, where we have months that are represented on the column. So those are all of the letters there, January through December. On the left side, you'll see those rows are labeled by brand of shoes. So this would be an example of a matrix that a manager of a local shoe store might use. This is the monthly sales for each of those different brands. And again, we can represent tables using the same labels and numbers and expressions, but the matrix takes that information and kind of takes away some of the extra information, and we read it the same way. So if I was going to look at this matrix and try to determine what this entry here would represent, this would tell me that we sold at the store 70 pairs of Nike shoes in the month of August. So again, it's very similar to a table in how we read the information when it's in a context. So we're going to be looking at just matrix as number representations and how we operate with those in just a second. So another thing to notice is that when we look at and work with matrices, we are using these brackets around the table of numbers, and that's again just kind of your notation for matrices, and so that people will know that that's what you are working with mathematically. So operating with matrices, the size of a matrix is determined by the number of rows and the number of columns. The dimensions are given in the notation number of rows first, then we use the X or the multiplication symbol in the middle, and then the last number would be the number of columns in the matrix. And so adding, subtracting, and multiplying a matrices are done just like we do numerically, with some different considerations, because if I'm working with a matrix that is a 2 by 2, and again we would know it was a 2 by 2 because of the number of rows and columns, I can only add another 2 by 2 matrix to that one, because I will be adding individual entries. Multiplication is a little different. We're going to study that on its own, but it is important to note how we set up and name sizes and dimensions of matrices. Because when we look at adding and subtracting two matrices together, they do have to be the same size so that I can combine each entry or element to the corresponding entry or element in the second matrix. Our solution matrix is again the same dimension, so if I was adding that 2 by 2 to a 2 by 2, the result would be a 2 by 2. And the two elements added together, so if I was adding the first row, first column to the first row, first column in the second matrix, those two things added together are placed in the first column, first row of the solution matrix. In the case that I'm trying to add two matrices or subtract two matrices that were not the same size, we would say that the operation is undefined, because we would have elements that could not be added or subtracted to an element in another matrix. So for example, 3, 1, 2, 9, 8, 7, 6, 5, 4, 3, 4, 5. So this is a 2 by 3 matrix being added to a 2 by 3 matrix, which means as a result, I'm going to have a 2 by 3 matrix. To get the 2 by 3 matrix that is a solution, I would add the 3 and the 6 from the first row, first column, together and get a 9. 1 and 5 would give me 6, 4 and 2 would give me 6, 9 and 3 would result 12, 8 and 4 is 12, and 7 and 5 is 12. And that is how I would add those two matrices together. In this example, I have a 2 by 2 matrix, and I'm subtracting a 3 by 2 matrix. Now, I can start and say 1 minus 4 is negative 3, 2 minus 5 is negative 3, but when I get to that last number, the 6, in that second matrix, I don't have anywhere to go because I'm missing an element there. And so this would be an example where we would say that that operation is undefined. So for matrix addition, our important properties that we need to make sure that we take into account and remember are the following. So matrix addition is defined by dimension of a matrix, being added together. So again, we're just saying that the two matrices have to be the same dimensions in order for us to be able to complete the matrix addition. The commutative property of addition for matrices, if I were to take and add matrix A to matrix B, it would look the same as matrix B added to matrix A. So just like numerical integers and their commutative property of addition, matrices follow that same commutative property. For additive identity, when we add and result in identity, that means that we have the same result. So the output is also the input. So I'm going to take matrix A, I'm going to add it to another matrix, and the result should be what I started with in matrix A. In order for that to happen, we would have to add a matrix of the same size that was what we refer to as the 0 matrix in order to get what we started with, because 0 is our additive identity for integers. So if I'm going to add something to an entry, the only way to get what I started with would be to add a 0 as a result. So it would be, if I was adding a 2 by 2, I would add a 2 by 2 matrix full of zeros as its additive identity. An additive inverse, just like we have inverse operations, is going to undo. So for additive inverse, we want to take a matrix, add something to that, so that in the end I get the 0 matrix. So for this to happen, every entry would be the inverse of the entry in the original matrix. The other operation that we're going to look at today is scalar multiplication. Scalar multiplication simply means that every entry in the matrix is multiplied by a number, and that's what we refer to as the scalar. So if you think about what you learned about in Math 2, when you scaled a geometric object and dilated it, you either made it larger or smaller, and you had to multiply each vertex of that shape in order to get your new output. So the same thing would happen here. If I scaled that matrix by -4, I still result in a 2 by 3 matrix, but every entry is going to have been multiplied by -4. So the result is a 2 by 3 with the entries -4, -8, -12, -16, -20, and -24. For this matrix, I'm taking and multiplying every entry by 2, so the result is still a 2 by 2 matrix. 2 times 1 is 2, 2 times 3 is 6, 2 times 2, 4, and 2 times 4 is 8.